Welcome to the ET335 Operational Amplifiers lecture video. This is a basic diagram of an operational amplifier, also known as an op-amp. And the triangular shape here on its side is the symbol for an amplifier. And this device has an inverting input and a non-inverting input. So the inverting is a minus, non-inverting is the plus. It also has a plus and minus power supply. And some of them also are a single-ended where they either have a plus and a ground or a dual supply with a plus and a minus. And here is the output. Here I'm showing the difference between an ideal and real-world 741 operational amplifier. The 741 is one of the original op-amps and is still around and still heavily used. We have an open loop voltage gain of infinite. So infinite gain, reality is about 100,000, which is extremely high. We have very large or infinite input impedance, about 2 meg. Output impedance is 0, it's usually around 75 ohms, which is quite low. Input offset voltage is 0. The real world is plus or minus 15 millivolts. Our bandwidth is infinite, but the limit is probably about 1.5 megahertz. Common mode rejection, infinite, and it's about 90 dB. Slew rate is infinite and about 0.5 volts per microsecond. And I'll cover these units later. Here are the internal systems of an op-amp. It starts with a differential voltage input, and basically op-amps are differential amplifiers, so they measure the difference between the two inputs, the inverting and non-inverting, and it multiplies it with the voltage amplifier stage. And then the final stage, which would be a push-pull amplifier, is basically for current, even though these devices don't produce a lot of current. Here I'm showing a single-ended input into our device. So we're putting an AC signal into the non-inverting, which is the minus, and I have a ground, and it's comparing these two. Unfortunately, with this amplifier, since we have the infinite gain, this signal, as this device is really no value because the gain is so large that it can't be used as an amplifier. So this is showing the single input. Here's another view of our single-ended. And without negative feedback, which I'll cover here in a little bit, is that these devices work as a comparator. So that the signal, no matter how small we put in here, since our infinite gain, it is going to multiply it to such a large value that it can't be used other than as a comparator. So if I put a plus 1 millivolt, it's going to drive it up to the maximum voltage. If I put a minus millivolt into the non-inverting, it's going to drive it to the maximum minus voltage. So without negative feedback, this device really can't be used as an amplifier. Here I'm showing an op-amp with negative feedback. So we have a negative feedback network, which is essentially going to be a voltage divider. And what we do is we feed back some of the output and feed it back into our inverting. So we're taking that signal, inverting it, which is going to subtract from our input, and it's going to allow us to control the gain of this device and make it useful. And this negative feedback, we could adjust it in order to control the gain amount. So this is negative feedback. Here is an inverting operational amplifier, and we have our input resistor and our feedback resistor. Okay, and this gain, AV is gain, A is gain, V is voltage gain. And we have our feedback resistance divided by our input resistance, and that's going to give us gain. Gain is unitless, and so we'll utilize that in order to calculate the gain, and then we could calculate the output voltage. And if you notice here, we have a sine wave input, and being this is an inverting operational amplifier, it's going to invert that output. So we're going to be 180 degrees out of phase. We're going to be opposite. And if I put a minus voltage in, it's going to come out as a plus, and it works the opposite way too. So whatever goes into this becomes inverted. So it's an inverting operational amplifier because the voltage goes into the inverting side, and is compared to the non-inverting, which is grounded. Here's an inverting operational amplifier with resistor sizes. So what we have is our gain is going to be 100 k ohm divided by 10 k ohm, which is going to be a gain of 10. And what we're going to do is we're going to take that voltage gain and multiply it by our input voltage, 100 millivolts. So 10 times 100 millivolts is 1,000 millivolts. And we could convert that to 1 volt. So we multiply that input voltage by our gain, which is 10. Here I'm showing a non-inverting amplifier. What makes this a non-inverting amplifier is our voltage input goes into our non-inverting side. Okay, and our formula is R feedback plus Rn plus 1. So it's going to be our regular feedback plus 1. So here, this is going into our non-inverting side, so our signal is going to be the same. So it's in phase, or if it's plus, it's going to come out plus. Here's our non-inverting operational amplifier with resistor sizes. So our gain is going to be 100 divided by 10, which is 10, and we're going to add 1. Okay, and we have 100 millivolts in. We're going to multiply it by 11, which is a 1,100 millivolts, and we convert that to 1.1. And our signal is going to be the same. It's going to be non-inverted. Here I'm showing virtual ground. If you read this in the textbooks, it can be a little bit confusing. But essentially what it is, because of this device, whatever is on the non-inverting side will be the same on the inverting. So since we're grounded, this is going to be the same, or essentially 0 volts. It's going to be virtually grounded. Okay, so if we go over here, we have our input current, which is our Vn, divided by the resistance, because this is 0. Okay, and then we get the input current, and since this is 0, we're going to get current here, and if we take this current and divide it by our feedback resistor, we're going to get our output voltage. Okay, so if I put in a bias voltage on our non-inverting, that would be the same at this point, and you could calculate it the same way. Here I'm showing inverting op-amp troubleshooting. If we were to lose our feedback resistor, that means that we have no feedback voltage. So we're going to have our infinite gain. So our output is going to be clipped and limited by our maximum voltage, which would be our rail voltage. And it would be a clipped sine wave like that. If the input is open, there's no way to get a signal in, so we get no signal out. Here I'm showing the non-inverting troubleshooting. So again, if our feedback resistor is open, we get infinite gain, and again we're going to clip our sine wave coming out. So it's going to be limited by the voltage or our rail. If we have a open here on our input resistor, we have our signal coming in, and the signal is going to go out and be the same. It's just going to go directly on through because we have no gain, because this feedback network is open. Here's another configuration of the op-amps. This is a unity gain buffer amplifier where we put an input in and we're going to get the same input out. It is used for typically for impedance matching. So our gain's going to be 1 and we're going to have a very high input impedance, which is good, and a very low output impedance. So if we were to attach a circuit to another circuit, this would be a good device in order to um, make very low impact on that signal because of the very high input impedance. If we need to change the input impedance, we could go ahead and put resistors in here and still have a gain of 1. Here's a summing operational amplifier, and essentially it's an inverting amplifier, and we're going to take individual channels in and we're going to utilize the gain of that pair and multiply it by the input voltage. So essentially this is going to sum up the voltages times the gain of each individual channel. Here I'm showing a difference amplifier. It's one of the many different types of op-amp configurations. And essentially we're going to take the gain and multiply it by the difference of the two inputs. And it's very important that these pairs are exactly the same resistance. And it's essentially going to multiply the difference times our gain. Here we have a comparator, and essentially we're taking our op-amp and removing all the feedback. And what it's doing is comparing these two inputs, and whichever one's larger, it's going to drive it to the rail. And the rail is the voltage of the power supply multiplied by some reduction depending on the device. They do have rail to rail, which is going to go all the way to the power supply, but most of them are limited to where the power is. So if I put a higher voltage in inverting, I'm going to go to the minus rail. If I put a larger voltage in non-inverting, it's going to go to the positive rail. So whichever one is larger, it's going to send it to that rail.